Hello everyone, welcome to the fourth lab of the semester. And the first thing that I want to talk about before even really getting started is that the last experiment over LRC circuits, it's technically titled LRC and Diodes, and the fourth experiment is called Diodes 2. And in the past, I believe that there wasn't enough time to do all the diodes parts in one lab, so they split it up. Even though when it came time to writing a report for the LRC circuit, the third lab, you didn't have to include any of the diode section as a part of the report. It's like the whole LRC part is self-contained, and then this diode section was just kind of tacked on. So instead, I decided to have all the diodes parts of the labs combined into one. So this is going to be the fourth experiment, but it's going to include part B from experiment 3. Now let's talk about diodes. Diodes are a component that have different effects depending upon their orientation relative to the flow of current in our circuits. And they can either be in a forward biased or a reversed biased orientation. Let's discuss what happens by looking at our characteristic plot that I've drawn up here in the left-hand corner, where I am plotting the voltage across the diode versus the current that's flowing through that diode. When a positive voltage is applied across our diode, like it would be in this orientation from this power supply, we see that no current is allowed to flow until we reach some threshold voltage, at which point current is freely allowed to flow through the diode. This threshold voltage is typically pretty small, like less than a volt, and we'll be measuring that in the experiment. Contrast this with the reverse bias orientation. So this is when a negative voltage is being applied over our diode, which would correspond to our circuit down here. No current is again allowed to flow through, although there is some leakage that occurs. But typically it's very small amount of current until again we reach some threshold point, and then the diode breaks down and current is again allowed to flow. The difference being that this is at a much higher voltage. And actually, so for different diodes, it can range from like 50 to over 100 volts, so it's pretty massive. But unlike the forward biased orientation, we actually typically don't want this to occur, because once the breakdown occurs for an ordinary diode, like this signal diode down here, then it breaks the component once it's an irreversible process. So that's something that we're going to be measuring in this experiment. So in actually the very first part, we're going to be plotting the voltage over our signal diode versus the current going through that diode to kind of recreate this plot for a signal diode. We won't actually be getting to this point where we see breakdown because it'll break our component, but we would like to recreate this plot right here. This other diode that we have here, this bigger one, is called the Zener diode, and it's similar to the signal diode with respect to the forward biased orientation. However, unlike the signal diode, for the reverse bias, once it reaches its breakdown point, it actually doesn't ruin the component. It's intended to break down, and it's a reversible process. So it breaks down at a much lower voltage than this kind of one that we would see for a signal diode, maybe around 3 volts or so. It's something that we're going to measure in the lab. This component is constructed in such a way that it's intended to break down and is a reversible process, and we're going to be using it in later experiments. In this lab, we're just going to be also creating a characteristic voltage versus current plot for the reverse bias orientation to see how it's different from a ordinary signal diode. The last thing that I wanted to discuss about this component is how you tell the orientation of a diode. So if you can see for actually both of them, this is the Zener and this is the signal. They have this black line on one side of the diode, and this will indicate what orientation that the diode is in relative to our power supply. So let me compare it here to this, the way it's drawn symbolically. So the way that I like to think about it is, again, it's forward biased when there's a positive voltage being applied, but also looking at the way that this circuit is being drawn, current would be traveling in a clockwise direction. That's what I usually use to orient myself, where the triangle, or the symbol here is a triangle with a line, and the triangle should be in the direction that current is flowing, and that would correspond to a forward biased orientation. And then if the triangle is against the flow of current, then it's the reverse bias. When it comes to actually putting the component into the circuit, well, I always match up this line that we have on the symbol with this line that's on the component. So if it were put in the circuit like this, where the black line is on the right, then it would be in a forward biased orientation. And again, flipped like this, where the black lines are matching up, would be a reverse bias. That's how I usually remember. I think that's it. Let's start the experiment. Okay, so this is part B of experiment 3, that diode section that I didn't go over in the previous video. So I've combined that latter section and all of experiment 4 into one. And in this part B, it's fairly straightforward. We are just recreating that characteristic plot of the voltage versus the current of our signal diode. So we're going to be making several measurements, both in the forward bias and reverse bias orientations, so that we can recreate those plots for our specific components here. So right now I have the forward bias circuit built, and just to trace through the circuit, we have current coming in from this positive lead, going through our forward biased diode, going through our 1000 ohm resistor, and then going to ground. So the reason why we need this resistor in series is that eventually, once we reach a threshold voltage, current is going to freely flow through the diode, and so if the resistor was not there, it would short circuit once we reach that point, and we don't want that to happen. Also, we're going to need this resistor to find the current going through our diode. So if we want to create this plot of voltage versus current, well, to find the voltage drop, it's fairly simple. We'll attach our alligator clips from our multimeter over it, and we can measure that voltage drop. But to find the current, we can use this resistor. So because these two components are in series and it's just a simple DC circuit, the current going through the resistor is going to be the same current going through the diode. So if we measure the voltage drop over the resistor and then actually measure its resistance, then we can calculate the current using Ohm's law. So before we actually start making our measurements, one thing that I would recommend is that you open up an Excel spreadsheet like you hopefully did for the previous video, so that you can very easily populate a column with the voltage across the diode, the voltage across the resistor, and then calculate the current, and then we can make a nice plot. But with that, let's start by measuring the resistance for our 1000 ohm resistor. So this is going to be my setup for the measurements. The multimeter on the left is going to be measuring the voltage across the diode, and the one on the right is going to be measuring the voltage across the resistor. Let's start by measuring our resistance for our resistor. So we'll just take it out of the circuit, and we have a value of 0.997, I guess. Yeah, we'll call 0.997 kilo ohms. So let me just attach this back in. A lot of wires. All right, I think that's good. And switch this so that's measuring the DC voltage. Okay, we are getting some reading for a voltage over our diode, but I think in general we can just have our first point be at 0, 0, because I don't actually have anything being output to the power supply. So 0 volts for our voltage drop over our diode, 0 for the voltage across our resistor. So the plan is to increase our voltage from our power supply so that we will read so that the voltage reading for the voltage across our diode is roughly in intervals of 50 millivolts or 0.05 volts. And so at 50 millivolts, we have, well, okay, so our actual reading is going to be 50.5 millivolts, and the voltage across our resistor is going to be 0. And so we will continue like that. So now at 100.8 millivolts, or 0.1008 volts, for the purposes of recording data and displaying it on a plot, it's probably more useful to record your data in terms of volts, so convert this scale to volts. Okay, so at 0.1008 volts, we get 0 volts over our resistor. At 0.1511 volts over our diode, we still have 0 volts for our resistor. 0 volts across our resistor. Let's go up by another 50 millivolts. So at 0.201 volts, we finally have a reading. It's 0.1 millivolts, or 0.0001 volts. Let's go by another 0.05. So 2.251 volts across our diode, and 0.0005 volts over our resistor. So 0.3003 volts over our diode, 0.0016 volts over our resistor. Let's go by another. I guess the closest we're going to get is that. So 0.3471 volts over our diode, 0.0041 volts over our resistor. We have 0.3997 volts over our diode now, and 0.0121 volts over our resistor. Let's go by another 50. Alright, looks like that's closest. So actually now our multimeter switched to being on the volt scale. So 0.448 volts over our diode corresponds to 0.0329 volts across our resistor. Let's go to 0.5. All right, 0.4989. 0.499 volts across our diode, and 0.0932 volts over our resistor. Let's make a couple more measurements. Okay. That's fine. 0.551 volts over the diode, 0.2707 volts over our resistor. Let's go to 0.6. 0.6, and then that corresponds to 0.723 volts. So we've definitely started reaching that threshold point now. Let's go up to 0.65 volts. 0.65 volts over our diode corresponds to 1.964 volts over our resistor. Let's make one final measurement. So you can actually see the current down here. This is a pretty rough scale, so that's why we're using our Ohm's law to calculate it from the resistor. So it's looking like it's around 0.003 amps. So I actually have the current limiter set, so it's at most our the amount of current that our power supply will allow is 10 milliamps, just so that we don't break anything. All right, so this is much bigger, so we need to go all the way up to 0.7. Okay, so at 0.7 volts over our diode, we have 5 volts, 5.06 volts over our resistor. So, very far beyond all of our previous data points. Okay, so that is all the measurements for this first part. I will now take this apart and make the reverse biased circuit and make the measurements for those. Okay, so here is the circuit in our reversed bias orientation. I've switched out the 1000 ohm resistor with a 1 mega ohm resistor, which we'll measure shortly. And if you notice, you can see this, I actually haven't changed the direction of the diode, still facing the same direction. What I have changed is the leads. So now that the red is on this right side, current's going to be coming in, going through this way, and now it's going to be going in that reversed bias direction. So I could have either done this or switched the orientation of the diode, doesn't matter. Okay, so for this set of measurements, whenever reverse, when you have a diode in this reverse bias orientation, it doesn't want current to flow through our diode. So the voltage drop over our diode is going to be very small until it reaches some breaking point and current just freely flows. And the problem with that is that it actually will break our diode. So we don't actually want to reach that point. And the voltage that we'll need to supply is, in order to do that would be big, like 50 volts. So we're never going to get there. But we want to see it kind of approach this point without actually getting to that, true breakdown point, because, we don't want to break our component. Because of that, the voltage drop over our diode, leading up until it breaks down, is really tiny. So unlike last time where we could just very easily measure the voltage drop over our diode and measure the voltage drop over a resistor, this time we are going to be measuring the voltage drop over the entire circuit. Then we're going to be measuring the voltage, and then we will still be measuring the voltage drop over our resistor. So we can take the voltage drop over this whole circuit minus the voltage drop over our resistor, and that should give us the voltage drop over our diode, because again, this is going to be very small leading up to that full breakdown point. We can start by measuring the resistance of our mega ohm resistor, attaching our leads, and then we can start with this round of measurements. So for our mega ohm resistor, guess we'll use this one. So our mega ohm resistor is coming in at 0.981 mega ohms. Okay, 0.981. So let's reattach. One other thing, if I kind of keep my, oops, sorry, just bumped the camera. I'm going to keep our alligator clips kind of in the same orientation so that the positive's on the left and the negative is on the right. So that because current's going to be flowing in the opposite direction of how we have our lead set up, we're going to get negative values, which is fine. That's, when we look at the characteristic plot for the reverse bias orientation, it's normally shown in negative values. So, ideally you could plot both of these reverse and forward biased plots on like the same scale, but you don't have to. Okay, so this one on the left, this multimeter on the left, is going to be measuring the voltage drop over our whole circuit, and the one on the right is still going to be measuring the voltage drop over our resistor. Okay, let me do that. So everything is set up, and we can start making measurements. So looking at the reverse bias section of the lab manual, it suggests that we start at our 2 volts DC on our power supply and go up to around 30 volts DC for and making about 10 measurements. Okay, so let's do that. So so last time I was referring to the voltage drop over our diode because that's what we were going to plot anyway, so I was just going in these nice steps of 50 millivolts. But because we're not directly measuring the voltage drop over the diode anymore, we have to find it. I'm just going to go in steps, equal steps on the power supply instead. So our first data point, like the last one, is just going to be 0, 0. Right now we're not outputting anything, so there should be 0 current and 0 voltage across our diode. So that can be our first point. And then let's start at, nope, don't want to change current. Let's go to 2 volts. So this will be our first point. So, and this brings up a good point. The voltage across our entire circuit should be close to whatever we're reading on our power supply. So we are reading a total voltage drop of negative 2.005 volts and a voltage drop over our resistor of 0.0044 millivolts. So the voltage across our diode would be, this minus this. Okay. So that can be our first point, and let's keep going. So up to 30. So let's just go to 6 and go in steps of 3, I guess. So negative 6.02 volts across our circuit and negative 0.006 volts over our resistor. Let's go to 9. Negative 9.03 volts over our circuit, negative 0.0068 across our resistor. Let's go to 12. Negative 12.05 volts over our circuit, negative 0.0076 over our resistor, negative 15.06 over our circuit, negative 0.0083 over our resistor. Let's go to 18. Negative 18.06 and negative 0.0092. Let's go to 21. Negative 21.07 and negative 0.0102 volts over our resistor. Let's go to 24. Negative 24.09 over our circuit and negative 0.0114 volts over our resistor. Negative 27.1 volts over our circuit and negative 0.0123 volts over our resistor. And last one. Negative 30 volts over our, negative 30.11 volts over our circuit and negative 0.0133. So that concludes part B from technically experiment 3. With those data points, you can plot the forward and reverse bias curves, those voltage versus current curves. Now we can move on to the actual experiment 4 and create those 3 circuits and move on. All right, so let's start on part A of experiment 4. And in this section, we are once again going to be creating a reverse bias circuit and going through this process of measuring the voltage drop over our diode and our resistor so that we can create this characteristic plot of the voltage versus the current for our diode. The difference now is we are using a Zener diode as opposed to the signal diode that we were using in the previous section. And we are only going to be measuring the reverse bias orientation because the forward bias is essentially the same as the signal diode, so there's nothing too interesting there. But the reverse bias, if you if you plotted out your data and or actually just looking at what we just measured for the signal diode, you saw that we had a voltage drop of up to like 30 volts, and there was no breakdown. And we didn't want to reach that breakdown because if we did, the diode would be ruined. It's an irreversible process once it breaks down. The Zener diodes, by contrast, are designed to break down. It is a reverse process. So we're going to be making similar measurements for our Zener diode and kind of finding where that breakdown point is and what it looks like. So to do that, we're actually going to be using 2 different resistors. If we look at the manual, looking at the procedure, kind of going through it, we're asked to initially get a 100 kilo ohm resistor and kind of go through a DC sweep of around a volt to 10 volts on our power supply, and then replace that 100 ohm resistor with a 100 kilo ohm resistor with a 100 ohm resistor and kind of go through the sweep again. So the reason for that is there are 2 regions for our Zener diode. If you remember back to the signal diode, we used a 1 mega ohm resistor, and even though we're using like this massive resistor, the voltage drop over our entire circuit was, it was still primarily over the diode, because we were up to like 30 volts, and then, but the voltage drop was huge compared to that of the mega ohm resistor. So this had a much higher resistance. The signal diode had a much higher resistance, and that's similar to what we're going to see with the Zener diode. So the the current is going to be really tiny, and up until that breakdown point, the resistance, or like over the diode, is going to be huge until we actually reach that breakdown point, and then we can use a much smaller resistor. Okay, so I think I will start by measuring both components, and then I'll call out when I switch out the resistors. So let's record the resistance for our 100 kilo ohm resistor. So it looks like it's 100.9 kilo ohms. And let me go ahead and get my 100 ohm resistor. Here we are. And looks to be around 99 point. All right, 99.1 ohms. We'll call it there. All right. So let me hook everything back up and start with the measurements. So similar setup to last time, where the multimeter on the left is going to be measuring the voltage across the diode. The one on the right is going to be measuring the voltage across the resistor. And right now I do have the 100 kilo ohm resistor in. So looking at the procedure in the lab manual in step 3, it asks us to set the DC power supply to 1 volt and go in steps of 0.5 volts on our DC power supply. So, and then measuring both their voltages across both components, and then getting the current from our resistor using Ohm's law. So I think it's easily displayed. So I will just go through all, 18 values, and have you record the voltages here. So these are only our important measurements. So first one. Oh, I'm sorry, and one last thing. So they are going to be negative again, because, well, one, it's going to be our reverse bias plot, so our value should be negative, but I have them, the leads are in the same way that I had it set up for the reverse bias for the signal diode, where I switched the leads while keeping the alligator clips for the multimeters in the same orientation. So we're getting negative values, but that's fine, because we are, that's what we want. So first data point for this section, 0.992, negative 0.992 volts for our voltage across our diode, and negative 0.0113 volts. This is right now in the millivolt scale, so make sure you oops, I didn't mean to zoom. So make sure you make note of that. All right, next one. Okay. Okay. 2.5. Let's go to 3. Okay, so now the multimeter switched to a volt scale, so now they're both displaying volts, which is convenient. Okay, let's go to 3.5. Let's go to 4. 4.5. 5. 5.5. 6. 6.5. 7. 7.5. 'All right, and last one, 10 volts on our DC power supply, and that's negative 2.997 volts over our diode and negative 7.04 volts over our resistor. Okay, so let me switch out our resistor with the smaller one, and we'll go through the measurements again. So I've switched out the 100,000 ohm resistor with the 100 ohm resistor, and looking at kind of the next part in the procedure, it's at step 8. It asks us to begin at 4 volts and continue sweeping in this 0.5 volt steps on our DC power supply until we actually reach our current limit of 10 milliamps. So you should see at some point we, even if we increase the voltage, it's going to stay constant, and that's because our current limit has been set. So let's go ahead and go to 4. Actually, just 3 look like. Yeah, let's start at 3 because this kind of corresponds to our last data point from the previous part, because I believe the voltage over the diode was around 3 volts and the voltage over the resistor was around 7 volts. So if this is negative 7 millivolts and this is a 100 ohm resistor, then it matches up pretty well. So we'll have this be our first point. Oh, don't die on me. Okay, we're fine. So we'll start here at 3, go in steps at 0.5 until our current limit is met. So our very first value or record for this setup is negative 3.004 volts over our diode and negative 0.007 millivolt. I'm sorry, negative 0.007 volts. It's 7 millivolts. So be aware that this is on the millivolt scale again. So, okay, that's our first point, and we will go in steps at 0.5 until we can't anymore. Okay, 0.5. Get a 4. Go to 4.5. Okay, looking at our, oh no, our, let's see, I think our, alright, that's fine. So that's 4.5, and we're already seeing 0.003 amps. Let's go up again. So now this is on a volt scale. So this data point is negative 4.56 volts across our diode and negative 0.444 volts over our resistor. Let's go another step. Okay, so this at 5.5. Okay, so that's that measurement. And okay, so now we've reached it. So yeah, okay, so 5.73 is the limit that our power supply is having it set it to. And so this will be our last data point. So negative 4.8 volts over our diode and negative 0.969 volts over our resistor. Okay. So with those points, or with those data points, you should be able to calculate, well, the current from our resistors, our two resistors, and we should have, or you should be able to plot that characteristic voltage versus current plot for our Zener diode. Okay, so that concludes part A of the experiment. With your data, you should be able to plot the voltage versus current plot of the Zener diode. So you should have 3 in all, between the 2 from the signal diode and the 1 from, combining your data sets, the one that you get from here. All right, so let's move on to part B. All right, so this is part B of the experiment, where we will be building various circuits and seeing how we can use diodes to change our AC signals from our function generator. This section is much more qualitative. I'm not going to be measuring any of the components. I'll make note of what they are when I'm going through the circuits, but you can assume that they're their theoretical values. We're going to be focusing on our outputs and switching out different components to see how it's going to change our circuit, but yeah, it's like I said, much more qualitative. A lot of describing what we're seeing on the oscilloscope. Okay, so this first one is, well, it actually looks quite similar to what we were just building with the forward and reverse bias measurements, where we have our current coming in from our power supply, or our function generator in this case, going through our diode, going through a resistor, and leaving. So this resistor is a regular signal resistor, diode, regular signal diode, where and for the rest of the experiment, we're going to, or the rest of the circuits, we're going to be using the signal diodes. The Zener diode will show up in later experiments, and we'll use that, its functionality for different circuits. But as far as the rest part of this lab, we're only going to be using the signal diodes. And this right here is just a 100 ohm resistor. So brown, black, brown. Okay. So let's take a look at our function generator. The lab manual suggests that we set it to 1000 hertz and somewhere between 2 and 3 volts peak to peak. I chose 3 volts, and I'll probably keep it at that 3 volts for all the rest of the circuits. I don't think this is changing. Yeah, it's for all of them. We can assume that our input is 1000 hertz and 3 volts peak to peak. And so let's take a look at this first circuit. So I've constructed this circuit on figure 6, which again looks like the forward biased circuit, but now that we're using an AC signal, it's also known as a half-wave rectifier. So right now, let's see what's happening. Oh, and I guess I'll point out that our yellow channel is our channel 1 is our input, so just the sine wave that we're getting from the function generator. Our blue channel, channel 2, is our output. So you can see here that we're measuring, this is downstream of the diode, this is measuring over the entire circuit. So that's why we're just seeing the input signal from the function generator. So this is what our output looks like. We have just a regular sine wave in, but actually let me scale this up a bit. We can see here that our output is only showing the top half of our waveform. So we can think about this is whenever we're in this top half of our waveform, when the circuit is experiencing this positive voltage, well, that's in the forward bias orientation, so it allows the current to flow. And then once it now is being switched, it's going in the reverse bias orientation, and there is just, our voltage output from our function generator is not enough to really bypass that diode. And even if it did, since it's a signal diode, it would break down because of it. So it allows first for positive half of the signal through, and doesn't allow the negative half of the signal. All right, so now our lab manual asks us to introduce this 0.47 microfarad capacitor in parallel with our resistor. You can see it in figure 7. So I've just jumped down this wire down to our capacitor. So now our V out is measuring over both these components, and our input is still the same. So let's see how introducing this capacitor changes what our signal looks like. I'll zoom out real quick. Okay. So if it's not immediately apparent that anything's different, I don't blame you, because it's pretty subtle. And maybe you can see it right here, how just the very, if I can actually stop displaying it, that so originally when it was just the resistor, this was pretty symmetric, but now we're starting to see this gradual slope. And maybe if I pull out the capacitor, so that's what I'm doing right now, you can see the change immediately, and it's much more apparent. So now I just pulled out the capacitor, and now I'm going to insert it back in. So let's talk about why we're seeing this change, slight that it is. In the forward bias orientation, we can see that we're still getting this half, the upper half of our waveform, and then in the reverse bias, and when the current's flowing the opposite direction of the diode, we aren't really seeing anything. We aren't seeing any voltage drop because current's not allowed to flow that way. However, charge has started to build up on the capacitor, and so even though the driving signal from our function generator is going in this reverse bias direction, the discharge from the capacitor is not. And we're starting to see how it is shifting ever so slightly to the right. And oops, sorry. So, whoops. Let's turn this off. So, and I guess if we wanted to scale it down so that they're both being represented on the same scale, that's what that looks like. But it's a little bit more apparent what's happening when we increase the scale of our channel 2 output. Okay, so let's now change up our components. In the next parts, in part 5 and 6, we are asked to exchange our 0.47 microfarad capacitor with a 4.7 microfarad capacitor, and then change our resistor to a 1K resistor. Now let me replace the 0.47 microfarad capacitor with the one that is 10 times as large. And so there. So with a larger capacitor, we can see that the discharge is sustained for a longer period of time, such that it can reach the next time that it's the circuit is entered the forward bias region. Okay, so our kind of half of our sine wave starts to look more like a stair step wave or a triangular wave, a sawtooth pattern. Let me now replace the 100 ohm resistor with the 1000 ohm resistor and see how the circuit is changed again. So there. And now, with the larger resistor, our AC signal has effectively been turned into a DC signal. And so much so that I believe if I were to, let's see, measure the mean voltage of channel 2, that we do get an average voltage rather than some rather than like an alternating, it's not a peak-to-peak signal anymore. Even though like our peak-to-peak voltage is really tiny, it's like 144 millivolts, but our mean voltage, which is essentially what is our DC signal, is now 600 millivolts. So that's what a half bridge rectifier does. It turns our AC signals into DC signals. Okay, so let me actually, just so you can get a good picture of it. So that's this part. Now let's build a full wave rectifier and look at its properties. All right, so here is the full bridge rectifier, which you can see in figure 8. If you were able to be here, this would have been the most complex circuit that you would have built so far. So let me just kind of talk about it, walk through the path that the current takes, and just kind of what's going on here. So maybe the first thing you notice is that I had to use the electronics kit board that I used in the first video because we needed to use this transformer. And down here, these leads are just from our function generator, and so this is being stepped up. So we're going to a smaller amount of coils to a larger amount of coils. So our peak-to-peak voltage from our input signal is being boosted. So we should see a larger peak-to-peak voltage value from when we measure the signal up here. And I'll show that once we are looking at the oscilloscope. But we don't necessarily want to use the transformer for boosting the peak-to-peak voltage of our signal. We primarily wanted to use it so we can have what it's called a floating circuit. We don't really want a ground in the full bridge rectifier, otherwise we won't get the desired effect. So let me trace through the path of the current. And this is still going to be an AC signal, so at one point the current's going to be going in this direction, and the other point is going to be kind of going in the opposite direction. So I'll talk about when the current is going this direction first. So if we look, current's flowing this way and it reaches this fork. And it can either go, whoops, can't block it. So it can either go over to this diode or down to this diode. Well, if you look, if the current is coming in this direction, well, this diode is in the reverse bias orientation. This is in the forward bias orientation. You can see by the black line here and here. So current will go through here, down through this one, and it reaches this fork. Well, now it can either go through this, jump to this resistor. And if you look on the figure 8, you can see that the resistor, this R1 resistor, it's a 10K ohm resistor, but it's kind of going around the circuit, but having it in between the two columns of diodes is essentially the same orientation. You know, if you look side by side, the lab manual and the circuit right here, you should see that having the resistor in between the diodes is the same as if it is, you know, how it's drawn there in the picture, in the circuit diagram. But anyways, so current comes down here, going through this diode, and now this diode is in reverse bias orientation relative to the flow of current. So it's going to pass through this resistor, and then it reaches this junction. Well, both of these are in the forward, you know, relative to a current coming in. Both of them are in the forward bias direction. So it can either go up or down, but going up will just kind of bring it back around again. So to complete the circuit, it'll go down here, continue around, and then go straight to ground. Or not ground, I'm sorry. It'll complete the circuit. There is no ground. That's the whole point. And so now the circuit is complete. Now let's look at when the signal is traveling in this direction. So it's traveling out. And this is kind of like the positive direction of our current. So coming out through this direction, we reach this, and now it can either go to this diode or this diode with this junction, and this one relative to a current going out, well, this is forward bias, so it's going to travel up here, and now it's going to reach this junction. So it can either go through this resistor or the diode, but relative to the current coming in, this is reverse bias, so it's going to go through the resistor. And then once again, we reach this junction, and the current coming in this way is also forward bias for both diodes. So if it goes down, it just will go right back up to you know, this diode, so it just like how it was in the previous one. So it'll go up here, and because this is forward biased, it will continue on and it'll complete the circuit. Okay, so that's roughly how current is flowing through the full bridge rectifier. Let's see what it looks like on the oscilloscope. So one thing that our lab manual points out is that we can't measure both our VN and our Vout simultaneously. And the reason for that is because it is this floating circuit and there is no proper ground, or there's no place to ground it. So right now our input is that we're going to measure is actually going to be over the transformer, because it's kind of like our this is our transformed signal from our function generator. So that's kind of acting as our pseudo power supply. So like I said, the transformer is stepping up our signal. So if we were to measure this signal, we have a peak-to-peak voltage of 12.48, or 12.5, roughly. Kind of bumped my. Okay. So our input signal is around, or it is 3 volts peak-to-peak, which means that this transformer is roughly quadrupling the peak-to-peak voltage. So that's consistent with the fact that it's being stepped up. And we can see that our frequency, which I am measuring right here, is unchanged. So that is our input signal for our circuit. So now to measure our output signal, we'll just simply measure over our resistor. So let me disconnect our channel 1 probe from the transformer and attach it to either side of our resistor. And so now if we look at our signal, it is reversed. Actually, well, to have it in the proper orientation, all I'm doing is switching around the lead with the, there it is, okay. So what I did was I switched the orientation. So now, this is our transform signal. So maybe you can notice what has happened. So our peak-to-peak voltage has roughly dropped by half. Our frequency has gone from 1,000 hertz to 2,000 hertz, so it's doubled. So this is half, this is doubled. I mean, roughly, this is 5 point. Maybe if I increase the... Nope, opposite's happening. Okay, well, it's halved, roughly. But you can see here that the negative, or what is like the negative part of our function, our waveform, has been flipped. So it's now being in this positive orientation. And that's because when I was chasing through the circuit beforehand, you saw that no matter if it's coming out one way or in one way, it always is, the way that the circuit is oriented, it's always conspired to turn the to return the signal into the same direction. So it flips this negative, but in doing so, if our waveform is no longer down here, I shouldn't point with my finger. If our waveform is no longer down here, then that explains why our peak-to-peak voltage is now half, because we're measuring between here and here, and our frequency has essentially doubled because a whole waveform was from originally our VN was from here to here, but now it's just there, or one whole cycle is whoop, right there. So this is how our this is the effects of our full bridge rectifier and how it can transform our signal. Now, to measure our output signal, we just have to connect our probes over the resistor in between the two. In between the two diodes. So now I'm measuring over the resistor, and we can see that our signal has changed. So, looking at our peak-to-peak voltage, it was around 12.5. Now it's halved, actually a little bit more than halved. It's now 5, but roughly halved, I guess. And our frequency has increased by a factor of 2. So looking at the signal, when comparing it to our input signal, our negative portion of our signal has now been flipped so that it's positive. And the reason for that is if you look back to when I was tracing through the circuit, no matter if the current was coming in from the red wire or from the orange wire, I can point it out. No matter if the current was going this direction from the yellow wire or orange wire, or coming in that direction from the red wire, it always passes through the resistor from right to left. So it either traces this way or traces this way. And because of that, it turns our, in this orientation, it turns our, negative part of our waveform, and it flips it up to the positive. So, and actually, if I were to now here, it doesn't say to do this, but I'll just do it real quick. If we were to instead switch the orientation of our probe, so now that it's measuring this to that side, what do you think should happen? I'll let you guess. All right, time's up. It does the reverse. So now it flips it so that the negative or the positive signal is flipped down. All right. So that is the effect of our full bridge rectifier. I just switched it back. So it's halved our peak-to-peak voltage, but it's increased our frequency because now our signal originally the period was, a whole cycle, I guess, was from here to here, but now it's half that distance, or you can think about it distance, it's half the time. So now it's just there. So it's twice the frequency. It's alternating twice as fast. So now let me go to this final part, part 8, where we'll introduce a capacitor in parallel and see how it changes the circuit. So now let me introduce the 0.47 microfarad capacitor in parallel with the resistor. So it's a little bit of a tight fit the way that I've built it, but it'll be okay. All right, there it is. So now we see that our alternating signal is effectively turned into a DC signal, kind of how the half-bridge rectifier worked. Although to get that same effect, we had to use a much larger capacitor. And on top, so what we noticed with the half-bridge rectifier is that it does turn this AC signal into a DC signal, but because our full bridge rectifier, before adding in the capacitor, already flips it, so it decreases the distance between our peaks, so the amount of time that is given for our capacitor to discharge is much less, so we can use a much smaller capacitor and effectively get the same kind of sustained discharge between our two peaks. So if you think about it, whenever we were doing the half bridge, it's like this middle one wasn't there. It was flat, peak, flat, peak, and so when we had to go from one peak to another, the capacitor had to bridge this gap. But now, with the full bridge, it only has to bridge this gap, which is, half as far. So let me put it back. So now it's an even more efficient way of turning a AC signal into a DC signal. And I think the final measurement that we need to make is to record the DC voltage level. So again, let me try autoing it, see what happens. It's all the way up there. Okay, so right down here we have our mean voltage as 3.44. So, and I think if I really zoom out, you can start to see the effects. All right. I think that's it for this section. Okay, so again, much more qualitative. We just kind of looked at how these diode circuits can change our AC signals. And that's it. I'll see you all in the next experiment. Have a good one.